Hello friends, welcome back. Today we will continue our discussion on UV visible spectroscopy and talk primarily about the principle of UV visible spectrometry. The session is planned as follows, that is, to begin with we will briefly recall what we did in the previous session. Thereafter we will try to differentiate between three very closely related terms, that is spectroscopy, spectrometry and spectrophotometry. Having done that, we will come down to the main theme of today's session, that is the principle of UV visible spectrometry. In this context, we will start by talking about the Boger-Lambert's law, and then thereafter we will come down to Beer's law and then build up the two together in terms of the Beer-Lambert law, because basically our main aim is to work out what is Beer-Lambert law and what is the significance of that. To do that, we will start with Lambert's law, then come to the Beer's law and then put the two together to get Beer-Lambert law. Having done that, towards the end we will try to sum up what we do in today's session. Let us begin by recalling what we did in the previous session. In the previous session, we basically started by defining what is UV visible spectroscopy and explained the origin of UV visible spectroscopy in terms of the transition amongst the electronic energy levels and things like that. Having done that, we talked about different types of species which are relevant from UV visible spectroscopy point of view, that is, what are the species, the organic molecules or the inorganic species which absorb this radiation and give a spectrum to us. Thereafter, we talked about that in all these kind of species, whether they are organic molecules or different kind of inorganic species, what are the possible kinds of transitions over there, and then these transitions, how are they getting affected by different factors over there. So, that was taken up towards the end of the last session there. Having done all this, in today's session we will try to see that how do I, we have just seen theoretically speaking what all is there. Now, I want to put things into practice. For that, we need to understand what is the principle of UV visible spectrometry. Okay. Now, to talk about the principle, prior to that let me just clarify to you three terms which are very commonly used. They are used interchangeably. We talk about what is called as a spectroscopy, spectrometry or spectrophotometry. These terms are used interchangeably, but they have got very delicate differentiation between each other. When we talk about spectroscopy, spectroscopy basically refers to the science or study of interaction of radiation and matter. So, that is spectroscopy, it is a branch which deals with that. When you come down to spectrometry, it is more of the measurement of the spectrum. Spectrometry, when the moment the term metry comes in over there, metry comes from the measurement part of it. That is, spectrometry basically deals with the science of measurement of the spectrum resulting from the interaction of radiation and matter. Spectroscopy is the study of interaction, that is one bit. But when you talk about spectrometry, we are basically referring to how do I measure the spectrum from the interaction of radiation and matter. And when we talk about spectrophotometry, that becomes slightly more specific. That is, if I am talking about a measurement of a spectrum involving visible light, then it is called as spectrophotometry. So, these terms actually are used very interchangeably, but we should be very clear about what are the terms we are using there and what is the significance of each one of them. And primarily in this course, we will be using the term spectrometry very often over there, because in all cases we are going to, whether we are going to talk about the molecular spectroscopy or the atomic spectroscopy, essentially we are, since we are talking about in the context of analytical determinations, we are going to make measurements over there. So, we will talk spectrometry more often than spectroscopy. Okay. Now, let us continue further and come down to the main theme of today's session, that is what is the principle of UV visible spectrometry. Okay. Now, let us see what do we do here. How do I get a spectrum there? What do? I take my sample which I want to make measurement of in some kind of a container. We will come to that in the next session in much more details over there, but for right now, as a matter of concept, we have a container which contains my sample there. Then I have a source of radiation, radiation is coming, interacts with this, and then it passes through that, some of it gets absorbed there. And then let's look at this picture here. What basically I am referring to here is that suppose I have this container here. In this container there is some sample which I want to make measurement of. So, what do? I pass some monochromatic radiation here of intensity say P naught, the radiance happens to be P naught. Okay. So, when this radiation comes in, interacts with this whole material here, that is the material of interest to me, that is the sample here, and also the container of it. So, what happens is when the two interact, some of the radiation get reflected back from outside the container also, they can get reflected back over there, which is shown in the blue arrows over here. When the radiation gets into the sample in the container there, then there is a possibility that part of it gets scattered like this, which is shown in the red arrows over there. There is another possibility that when this radiation interacts with the other end of the container, there again can be reflection over there. And then after all this happens, part of the radiation gets absorbed and something which comes out over there. So, there are different components in this. That means, we have incident radiation coming there, there is a reflection there, there is scattering, there is transmission here, and then rest of it is absorbed there. So, all these possibilities are there. Okay. Now, in terms of our quantification, in terms of quantitative kind of application of this, we need to understand what is the relationship between P naught and P, because when you do it experimentally, we are primarily trying to minimize the effects of reflection and scattering. Having done that, we find that there is a relationship between P naught and P, which actually are related to the analyte over there. We will see what are the relationships over there and how do I make use of that in terms of the quantification of the analyte. Okay. Let us go further and see that when I take a sample, put some radiation on that, and then the radiation which is coming out, that is the transmitted light which I want to make observation of. That means, we have incident radiation, there is a transmitted radiation there, and we find that this transmitted light which comes out after the sample happens to depend on the intensity of the incident radiation, that is P naught, and second is the concentration of the analyte. That means, how much of the material is there in the container there, and the third component happens to be the thickness of the absorbing medium. Say this is my radiation coming there, this is my sample here, radiation comes in here, this is my P naught coming, what comes out from here is P. Okay. What do I do next is I take maybe a higher thickness, now the medium is larger now, radiation comes in over there P naught, what comes out from here will be maybe P prime. So, that P prime and P are different from each other, because now the radiation is passing through a thicker medium over there. That means, there are more molecules which are interacting with the radiation, there is a more absorption possibility there. Okay. Now, essentially, if I want to put all these things into application in terms of quantification, I have to find out some kind of relationship between P naught, that is the incident radiation intensity, P the intensity of the transmitted light or transmitted radiation, C the concentration of the sample I am taking there, and B that happens to be the thickness of the medium wherein I am taking the sample over there. And all these are related in terms of what is called as the Beer-Lambert's law. So, that is the main theme over there. Essentially, it boils down to the fact that if I want to talk about the principle of spectrometry, essentially comes down to that understanding what is this Beer-Lambert's law, because that is the one which is the most crucial law to be understood over there. Okay. Then what is this Beer-Lambert law? Let us see that. Beer-Lambert law essentially is a combination of two laws. One is called as a Beer law, other is a Lambert's law. And chronologically speaking, the Lambert's law or the Boger-Lambert law came prior to the Beer's law over there, and this basically relates because there are three things there. There is P naught, there is P. Okay, we are trying to find out relation between P naught and P, and there are two variables over there. One is the concentration of the medium, and second happens to be thickness. So, there are four terms there which have to be related there. And this Lambert's law basically relates that this intensity of P which is coming out after passing through the medium, that will depend on the thickness of the medium there. That means, it relates light absorption and the thickness of the medium there. On the other hand, the Beer's law, that relates light absorption and the concentration of the medium there. So, there are two things there, because there are two variables I said, one the thickness of the medium, two the concentration of the medium there. So, one of these laws relates with the concentration and one relates with the thickness of the medium there. Let us talk about the Boger-Lambert's law. Basically, this law was discovered by Pierre Boger around 1729, way back, but it was not documented, so to say, and this was documented by Lambert in about 1760, about 35 years later. And Nowadays, typically this is attributed to Lambert only, but of late we started putting a hyphen over there and we started calling about Boger-Lambert's law. Earlier it was just called as Lambert's law. Okay. Now, what is this law? This law basically is states as follows, that is, the amount of monochromatic light absorbed by substance is proportional to one, intensity of the incident light or the radiation there, and second happens to be the thickness of the absorbing medium. So, that is the basic statement, or so to say, of this law there, that is, the amount of radiation which is absorbed, that will depend on the two parameters there, intensity which is coming into this, and secondly thickness of the medium there. And let us look at this here. This picture basically shows, I have taken actually the cuvette, the container I was talking about earlier, I have taken a blown up portion of that. In that what you see is that this is a highly stretched out version of that. What you find is that this is P naught, there is an intensity which is falling in the incidental intensity onto the container there. Then this P happens to be the intensity of the transmitted light or the radiation there. And in between that, I just made a small slice of the sample compartment over there, which is shown as of a thickness as dB. And this is the intensity which is coming over there, say P, this is P minus dP. So, this Z basically is telling about the direction part of it, that is the material here. So, how does this statement translate into a mathematical expression is something like this, that is dP is the decrease in the intensity. That means you have a container like this. So, let us imagine this is a container I am talking about, radiation is coming here P naught, it comes out from here P. Now, suppose within this container I have a small slice here. Now, at this slice the incident radiation happens to be, say, some intensity Pz. What comes out from here is Pz minus dPz. This dPz, the small decrease in the intensity when it passes through a very fine medium there, that is of thickness dB, that is equal to dP here. I am just omitting Z over here. Z basically it could be X, it could be Y, it could be Z, that it depends on the direction of it. So, I am just skipping the direction part of it here. So, we can write out that dP to be equal to minus of K, K happens to be the proportionality constant, because dP is the decrease in the intensity is proportional to P and dB. So, and then if I remove the proportionality constant over the proportionality there, I replace by a proportionality constant here. That means, the expression now comes is that dP is equal to minus of K P dB. Minus tells me that there is a decrease in intensity. K is the proportionality constant, P actually is the intensity which is incident over there, and dB is the thickness of the slice I am talking about here. Now, if I integrate this expression over the whole thickness, that means from P naught to P, if I do that, we get the following expression. This is a mathematical expression for the Lambert's law or Boger-Lambert's law, that is log of P naught by P is equal to K by 2.303B, and this K is a constant here. So, 2.303 is a number. If we divide this, this becomes a new constant over here. So, we can write log of P naught by P to be equal to K prime B, where K prime happens to be a constant there. So, that is the mathematical expression for the Lambert's law. What does this signify? Let us see that. If I look closely at this expression, we find that on left hand side I have got a term like log of P naught by P, whereas on right hand side I have got K prime B. That means, this shows there is some kind of a logarithmic relationship coming into play. What it means to say is, that is, the intensity of the transmitted light decreases exponentially when the thickness of the medium increases linearly. That means, when the medium becomes thicker and thicker, intensity will go on decreasing very, very sharply over there. Intensity does not decrease linearly there. Let us understand that. Now, if I have, let me imagine that I have a cuvette of a thickness say equal to B, and if I give a radiation of 100 intensity of 100 units over there, and let me assume that there is a decrease of 25 units when it passes through B. That means, when the radiation comes out of it, it will be 75. Now, suppose it is like this, I would expect, if it is a linear relationship, that now if 100 passes through, I will get 50 from here. If this happens, I will get 25 from here. If this happens, that means my thickness becomes 4 times. If 100 comes in here, I should not get anything over here. But what we get in according to this law is as follows. There are 4 cells I have made here of each of thickness equal to B. Now, according to this law, what happens is, if on the first chamber over there intensity of the radiation which is falling on it happens to have 100 units there, and if I assume the same thing again, that is it decreases by 25%, that means when it passes to the second compartment here, the intensity will be 75 because 25 have been decreased over there. But when it goes through the next compartment here of again thickness equal to B, again there will be reduction of 25% over there. That means from 75, if I decrease 25% of that, that will come out to be 56. It goes further, again there will be decrease of 25% there, from 56 it will become 42. Next compartment it will be 32. That means when the radiation comes out here, after travelling a distance of equal to 4 times B, I will get an outcome of 32 units there. That means the intensity will be 32, which will be coming out there, and started with initial was 100, what comes out will be 32. If it was a linear relationship, I would have expected if 100 comes in there, I will get 0 over there. So, that is the difference over there. That means the intensity does not decrease linearly when the thickness increases linearly. Intensity decreases exponentially. That is the significance of this whole expression over there. Okay, let us go further. Let us go further and now come to what is the second important law, that is the VIS law. Lambert's law related the intensity of transmitted light with the thickness of the medium. VIS law does the same thing between the intensity of transmitted light and the concentration of the solution there. And again, I will not go into details of this because now we have understood how do we go about it there. It is just a parallel treatment of what we did in the case of Lambert's law here. And we come to the following expression over there, that is the intensity of the transmitted light decreases exponentially when the concentration of the absorbing medium increases linearly, parallel to what we had in case of Lambert's law. And the mathematical expression for the VIS law comes out to be the following, that is log of P naught by P to be equal to some other constant k double prime divided by 2.303 into C. Now we have C as a concentration term over there. Earlier we had term B, which was thickness of the medium there. And if I put the two together there, that is k double prime by 2.303, this comes out to be another constant here. So, k triple prime C, essentially log of P naught by P is equal to a constant into C there. Exactly a parallel expression what we had in case of the Lambert's law there. But now when we talk about the interaction of radiation with the matter which is taken into cuvette, we have both the components over there because the medium has a thickness of B and there is a concentration as well there. So, we combine the two laws together, that is the VIS law relating transmitted light with the concentration and Lambert's law related with the thickness there. When the two are put together, we get what is called as a Beer-Lambert's law. And Beer-Lambert law can be seen as essentially, as I mentioned, it is a combination of Lambert's and the Beer's law there. It relates the attenuation. Attenuation basically means the decrease, the absorption, the decrease in the intensity of the radiation with the concentration and the path length of sample there. We will not get into details of that. We can just straight away say that we can put expression to be equal to log of P naught by P to be equal to ABC. Let us understand what is this ABC here. One expression we had was log of P naught by P equal to a constant K into B. Second was log of P naught by P to be equal to another constant K triple prime into C there. When the two are put together, what you find is that we have a combined expression as log of P naught by P to be equal to A. This A actually is made up of both the constants there, K prime, K double prime, whatever the constant we take there, they all are subsumed into this constant A there. This is a very, very characteristic constant here. This is called as the absorptivity. A is called as absorptivity and B we know is the thickness of the medium there and C happens to be the concentration of the absorbing species there. So, this is a very, very crucial and very, very important expression for us because that we are going to use extensively when we try to put this UV visible spectroscopy for quantification of the analyte there. Okay, so, let us go a little further into this expression there. Okay. Now, if we take the concentration is expressed in terms of grams per decimeter cube, that is typically done, and thickness happen to be B, which is a symbol for that. Typically, thickness of the medium is expressed in terms of centimeter there. If that be so, that means if the concentration of the material I am taking has the following units there, gram per decimeter cube, and thickness happens to be in centimeter, then A, absorptivity will have the units of centimeter inverse, gram inverse, decimeter cube. That is very crucial there. But more often than not, we use the concentration in terms of mole per decimeter cube. If I take concentration in terms of mole per decimeter cube and B happens again in centimeter, then absorptivity is called as molar absorptivity. That is a special term given to that. That is, when I am taking concentration to be in mole per decimeter cube. And then this also has been given a special symbol called as epsilon, and this has the units of centimeter inverse, mole inverse, decimeter cube there. This is very important here, because one has to be very careful, because they will be coming across a lot of, we will try to solve some problems on that. So, when you try to solve these problems, we try to put this expression into use, we must bear in mind what are the units over there. This is very, very important there. This epsilon actually, as I mentioned just now, is called as molar absorptivity. There is an older term, if you look into the older books there, they will call it as extinction coefficient. It is not to be used any further. You might find that term in the older literature. Please do not use that term, because that is not acceptable by IUPAC. Okay. Let us go further. Let us go further and then see that if I am using the concentration in terms of moles per decimeter cube, and I have A absorptivity now becomes molar absorptivity. The other expression now gets modified to the following expression over there. That means this is the expression for Beard-Lambert law if I am using concentration in terms of mole per decimeter cube. This molar absorptivity epsilon, actually this is a very, very characteristic property of the system I am talking about, the compound, the material, organic compound or the inorganic species, whatever I am trying to analyze there. This is very, very characteristic of that, and it does not depend on the concentration or the path length. It is an intrinsic property of the species I am trying to analyze over there. And what we see further is there is one more very important term which we will be using very often on the left hand side of the expression over here, log of P naught by P has been given a special name called as absorbance, and the symbol is A for that. That is, A absorbance is equal to log of P naught by P. If I substitute this over here, what do I get is the following expression, that is log of P naught by P is equal to A is equal to ABC or epsilon BC. That means A is equal to ABC is the expression A absorbance, A absorptivity, B thickness, C concentration. A absorptivity if C happens to be in gram per decimeter cube there, and E epsilon to be equal to molar absorptivity if C happens to be in mole per decimeter cube. So, this we had to be very careful about. Okay. So, I am just trying to highlight this fact over there, that this is the most crucial expression we have for our Beard-Lambert law, which we will be using very, very often there. Let us go further and talk about a few more important terms over here, and one of them happens to be what is called as transmittance. Transmittance is nothing but the ratio of P to P naught. P is the intensity of the transmitted light and P naught happens to be the intensity of the incident radiation over there. And if I just try to rearrange a little, we find that A, the absorbance what we talked about a little while earlier, is equal to log of 1 by T, because there we had the reverse of that over there. So, this comes out to be minus of log T there. That means A is equal to minus log T is again an important relationship which we will be using there. And yet another important term happens to be percentage transmittance, which is nothing but transmittance expressed in terms of percentages there. So, percentage transmittance will be equal to P by P naught into 100 over there. Let us try to solve some simple problems based on Beard-Lambert law, and the first problem we take up is, that is, accounting for solvent absorption. A 3.6 × 10⁻⁴ molar solution of a given compound X taken in 1 centimeter cuvette had a absorbance of 0.545 at 267 nanometer. So, that is the information given to us, and we are supposed to find out the molar absorptivity for the system over there for the compound X. How do we go about it? How do we go about it is, that is, we see that we are given the following information, that is, concentration is known to us, path length is given to us, that is about 1 centimeter, and absorbance also is given to us, and we need to find out epsilon, the molar absorptivity. So, how do I go? I just take recourse to the Beard-Lambert law. We know that Beard-Lambert law tells me that A absorbance equal to epsilon B C. So, there are 4 parameters there, A, epsilon, B, C, and out of these 4 we know 3 of them. We know C, we know B, and we also know A. So, what we do is we just rearrange this expression in terms of the following way, that is epsilon, that is molar absorptivity, is equal to A absorbance by B C. B is the thickness, C is the concentration. Then it becomes very straightforward. I just make simple substitution of the given values there and just solve it. What do I get is, I get the following expression there, that is 0.545, that is absorbance given to me, 1 centimeter is the thickness, and this is the concentration given to me. I substitute them, solve it there. What do I get is, I get expression the value as 1514 centimeter inverse mole inverse decimeter cube. So, that is the molar absorptivity of the compound X over there. Very, very simple application of the formula there. Let us take one more simple problem over there. Let me take the same compound X again. Now, I want to find out what concentration of the solution of the compound X in the same solvent as we had in the first example there, taken in a cuvette of 2 centimeter now. Now, I have increased the thickness of the cuvette there, would have an absorbance of 0.374 at the same wavelength over there. So, in this case, what do I have? I have been given the following information. I have been given path length to be 2 centimeter and absorbance also is given to me. And we know from the previous example number 1, that is what is the epsilon value which we actually computed in the as a problem in the first example there. So, again we have 3 knowns to us. We know the path length, we know absorbance, we know epsilon there. Again we take recourse to the Beer-Lambert law, that is A is equal to epsilon BC. So, I need to know C now. So, I take C on the left hand side and rearrange the equation over there as C to be equal to A by epsilon B. I know A, I know epsilon, I know B, I substitute them and just solve it. What do I get is, I get the concentration over there. So, we find that essentially it boils down to that Beer-Lambert law had got 4 parameters there: absorbance A, mole absorptivity epsilon, thickness B, and C the concentration there. We keep the units of the expression in mind, and then out of these 4 parameters, if I know any 3 of them, I can find the 4th one. So, that is the basic premise on which we try to solve problems over there. Now, let us sum up what we have done today. What we have done today is, we started by reviewing the contents of the previous session, and then thereafter we differentiated between 3 close related terms, that is the spectroscopy, spectrometry and spectrophotometry. Having done that, we came down to the main theme of today's session, that is the principle of UV visible spectrometry, and in this context we talked in detail about the 3 important laws, that is Lambert's law, which relates the intensity of transmitted light and the thickness of the medium there, Beer's law which relates concentration and the transmitted radiation there, and Beer-Lambert law, the 2 put together over there. Thank you.